Okay, good afternoon, everyone. My name's Patricia Whitelock, and it's my very pleasant duty to welcome you today and to introduce the speaker. This is an extraordinary meeting. It's a joint meeting of the South African Astronomical Observatory, the Academy of Science of South Africa, and the Royal Society of South Africa. And this joint special occasion is because of our guest, vying to introduce our guest, Michele Dougherty. Michele was born in South Africa and educated and did her university education at the University of Natal before moving to Germany and eventually to Imperial College London, where she is currently a professor of space physics and was, I gather, until a couple of months ago, head of the department, head of the physics department. She's had an extremely illustrious career, mostly involved in space exploration of the satellites of the gas giant planets, which she's going to tell us about in a moment. And this has led to her recognition in various ways. She's a fellow of the Royal Society of London, as well as of the Royal Society of South Africa. She has won various medals from the Royal Astronomical Society, the Royal Society. She's also a member of the American Academy of Arts and Sciences, and unusually for a scientist, a commander of the British Empire. She is also president-elect of the Institute of Physics. And we're really delighted to have today Michele Dougherty, who's going to tell us about discoveries of the icy moons of Jupiter and Saturn.
Tricia, thank you very much. And it's really nice to come to the We were quite concerned because it's so cold and horrible out there that we might be the only people in the room. So thank you so much for joining us. So this evening, I'm going to tell you about two of the spacecraft missions that I've been involved in, both of them linked to the outer planets. The first one is called Cassini, and it visited Saturn. It's been 13 years orbiting around Saturn. And I love that particular image on the right, because it showed you a composite of lots of different images that were taken by the camera on board Cassini over a long period of time. And it shows you the planet itself, the visible rings that you can clearly see. It also, and the trick will be if I can get this mouse to work, it also shows you a ring called the E ring, where if you look closely, you can see that there's actually a moon within that E ring called Enceladus. And one of the discoveries that my team made on the Cassini spacecraft is that that E ring was outgassed, that moon was outgassing water vapor. And so I'm going to describe that discovery to you. But I think for me, the cutest thing about this image is if you look closely where my pointer is, that is the Earth. And so it makes the hair on my arm stand up right, because here was the spacecraft orbiting around Saturn, taking pictures of Saturn, but it saw us on the Earth. And then on the left, we've got a view of Jupiter, and I'm going to talk during the presentation now, a little bit later, about a mission called JUICE that's on its way to Jupiter and the icy moons. So let me talk about Cassini to begin with. This shows you an image of the Cassini spacecraft, and it shows you all the different countries that were involved. On my team on Cassini, I had scientists from the UK, from America, from Hungary, and from Germany. But you can see for a spacecraft mission as large as this, you need to have international involvement. And you can see how many different countries were involved as far as scientists and engineers. So the Cassini spacecraft went to Saturn. It orbited around Saturn. But in addition to that, it had a probe called the Huygens probe. And this probe here was built by the European Space Agency. So the Cassini spacecraft was built by NASA in the US. The Huygens probe was built by ESA, the European Space Agency. And this Huygens probe here that I'm pointing out with the mouse actually was detached from the spacecraft and traveled down through the atmosphere of one of the moons called Titan. I'm going to talk about Titan to you in a moment. This white umbrella-shaped thing is known as the high-gain antenna, and once a day when we were orbiting around Saturn, we would point to the Earth and it would send the data down that we'd got the previous day. And this long boom here is the magnetometer boom. And what we do at Imperial College is we build instruments that measure the magnetic field. And if you want to measure the magnetic field of the environment you're in, you want to be as far away from the spacecraft as you can. So that's why we put ourselves on this very long boom. And so there were two different instruments. One of them was halfway down the boom here, and one of them was right at the end of the boom. The other thing you might notice is everything's covered in gold foil. That acts as a thermal blanket. It helps to keep the instruments in the spacecraft at temperatures they can actually operate at. This shows you a view of the Cassini spacecraft in the test chamber at Cape Canaveral before launch. And there are a couple of reasons I like to show this one. First of all, you've got some people standing in the image, so you can see how big the spacecraft was. In addition to that, you can see that the magnetometer boom that my instrument was on essentially doesn't seem to be there. And that's because it was folded away in this canister here. Because if you think about it, you can't launch a spacecraft with a large boom sticking off from the side. And so what happened is after we were launched, the boom was deployed. One of the reasons we were in this test chamber here is it allowed us to test that the instruments in the spacecraft could operate in the vacuum of space that they would need to operate in. But also we were able to test they could operate in the vast range of temperatures that they would see. So we flew past Venus, seems strange, go in the inner solar system, but we flew past Venus to get out to Saturn, and there the temperature's about plus 40 degrees Celsius, and then out at Saturn it's about minus 170 degrees Celsius. So we needed to test all the instruments. Okay, so what I'm going to do this evening is I'm going to talk about some of the magnetic field observations that we measured. And to be able to do that, I just wanted to describe to you what it is that the instrument measures. But this shows us a view of the Earth. It's the same for Jupiter and Saturn as well. So if you stand on the surface of the Earth with the compass, the needle of the compass is going to point to the North Pole of the magnetic field. And so on the Earth, we have this magnetic field that is generated in the interior here. These red lines are the magnetic field lines. You can't see them, but that's what my instrument is able to measure. And so you can measure these magnetic field lines, and they allow you to get an understanding about what's going on inside the body, but it also gives you an understanding about what's going on outside as well. One way to think about it is if you've got a piece of paper and you've got a bar magnet underneath that piece of paper, you put iron filings on top. The iron filings are going to lie along the lines of force of the magnet, and that's essentially what the magnetic field is. The other thing I want you to keep in mind as I take you through one of the discoveries that we made is as a planet rotates, so as the Earth here, or Jupiter and Saturn, rotate once a day on the axis, the Earth rotation rate is once every 24 hours. On Saturn, it's once every 10 hours. Those red lines are going to rotate at the same rate. And so if you're a body away from the planet, those red lines are going to move towards you. And depending on how they behave, you can get an understanding about what kind of body you're actually looking at. And so that's what we used to make the discovery that we did. So this here is a view of Saturn and its rings and all the moons. So here we have Saturn, we have the visible ring here. We have this very diffuse ring, the E ring that I pointed out to you in the first image. And then you've got the different moons of Saturn that orbit around it. So Enceladus is the moon that I'm going to be talking about now. But before I move on to the next slide, just want to point out Mimas and Tethys. Those are two moons that orbit inside of Enceladus and outside of Enceladus, and they orbit around Saturn. And I'm going to mention those in a second. Now, two things I wanted to say before I move on to the next slide is the E ring, this diffuse ring that you can see here, is very large, but you can't see it very well until you actually get into orbit around Saturn. And it turns out that the particles in the E ring are made up mainly of water ice. And that's something to keep in mind when I talk to you about Enceladus. So this here is a view of Enceladus, which was taken by the Cassini camera. It's two different images that were put together. One of the first things you'll notice is there are a few craters on the surface, but there aren't very many craters. And that's really different compared to Mimas and Tethys that orbit close by to Saturn. These surfaces are covered in craters. And so the implication is that something is happening at Enceladus to make the surface younger. Something is resurfacing it. You'll see there are some cracks, some very deep cracks on the surface. But the real surprise was the fact that the surface is as young as it seems to be. Now, before we had these Cassini flybys in Enceladus, we'd always wondered whether it might somehow be the source of the E-ring, because there was a NASA spacecraft called Voyager that flew past Enceladus in the late 70s. And it had an instrument that was able to remotely sense what the surface was made up of. It was made up mainly of water ice. And we knew that the E-ring was made up mainly of water ice. So we always wondered whether somehow Enceladus was the source of the E-ring, but we weren't quite sure how that might happen. So we went into orbit around Saturn with Cassini in July 2004. And in early 2005, we had 3 flybys of Enceladus by Cassini. And these were the distances of the spacecraft away from the surface of Enceladus. The first one was quite a distant flyby, just under 1,300 kilometers from the surface. A month later, we had a second flyby, which was 500 kilometers away. And then based on what we saw on these first 2 flybys, we were able to persuade the Cassini project to take us much closer on the third flyby. So the third flyby was 173 kilometers above the surface. And before I move on, one of the things to keep in mind about Enceladus is quite small. Its diameter is only 500 kilometers. Oh, you can go back. I'm giving it away. Giving it away. So, on the first flyby, we saw something strange. We saw something in the data that we couldn't quite understand. And to begin with, I must confess, I thought that we hadn't calibrated our data properly. I thought that maybe we needed to understand how the instrument works a bit better. And so within the team, we talked about the fact that we'd seen a strange signal, but we didn't tell anyone else. A month later, we had the second much closer flyby, and we saw a similar signal. And one way to describe the signal is what I gave you a hint on. So the 2 different views that we're looking at here. So in this first view, if you look at the top right, what your eye is doing is looking down on the North Pole of Saturn. So here's the North Pole of Saturn. So the orange ball, or the yellow ball is Saturn, the gold rings of the visible rings of Saturn, the blue lines are the magnetic field lines of Saturn that are rotating once every 10 hours, and the little orange ball is Enceladus. Now, if Enceladus was a dead body, which we thought it was, the magnetic field lines of Saturn, the blue lines, we wouldn't see it at all. They'd move straight through, and we would see nothing in our data. But what we seem to be seeing in our data was the following. And now your eye has moved. Now you're looking sideways on. So here your eye is, and you're looking sideways on Enceladus. So there's Enceladus, and these are the blue lines coming from Saturn. And what our data seemed to be telling us, that Enceladus was draping around the moon. Something was stopping it from penetrating down through the surface. And one way that you can do that is if you've got an atmosphere. Because just like on the Earth, the upper regions of our atmosphere become ionized, they become a plasma, and they stop the solar wind and the magnetic field from the solar wind penetrating down. So they essentially protect the Earth from the effects of the solar wind. So that was one way we could describe the observations that we saw. So what I did is I went out to the propulsion lab, and I gave a presentation to the project describing what it was that we saw. And I didn't know if I'd be able to convince them that we thought we were seeing something interesting, but it was really quite sweet. I arrived and I was jet lagged because it's an 8-hour time difference. And I was standing in a line to get a Starbucks coffee before I went in and gave the presentation. And there was a man standing in the line in front of me. Turns out he was responsible for the safety of the spacecraft and for deciding where it was going to go. And he turned around and he said to me, "Michele, what are you doing here?" And I told him. And he rubbed his hands together and clearly said, "Well, that's cool. I've always wanted to go closer to a planetary body than anyone else." So I knew I had one vote in my pocket before I went into the meeting. So I went into the meeting and I described what we thought we were seeing. So what I said we thought we were seeing is that Enceladus was covered by a diffuse extended atmosphere. The upper regions were becoming ionized, and that was causing these magnetic field lines of Saturn to drape around Enceladus. And what I asked for was that the next flyby 3 months later would be much closer, so we could really get close and see what was going on. It took a bit of persuasion, because what that meant was we would need to use some spacecraft fuel. You always want to keep fuel so you can extend the mission at the end. But also, in the 6 years it took us to get to Saturn, we planned every single second of the observations we were going to make when we got there. So that means some of the instruments would not get the data that they were planning. But eventually the decision was made that we would take the chance. So the Cassini project agreed they would use some fuel to take us much closer on the third flyby. And fortuitously, you'll see why I say that in a moment, the third flyby took place just below the south pole of Enceladus. And I must confess, for 2 or 3 days before that third flyby, I didn't sleep very well, because if we'd seen nothing, no one would ever have believed anything I said again. But luckily, this is what we found. So instead of there being an atmosphere covering the entire surface of Enceladus, we had this plume of water vapor, essentially coming out from the south pole, spewing out large clouds of water vapor coming out. And because we went so close, all the other instruments were able to take great data as well. So let me show you data from some of those instruments. So this is data from 2 different instruments. In the top left, we have the imaging camera, which show these cracks at the south pole that the team called Tiger stripes. Bottom left, we have data from an instrument that's able to remotely sense the temperature of the surface. And they expected the hottest temperature to be at the equator, because that's where the solar radiation is strongest. And yes, it was hot at the equator, but at the south pole, there was this huge hot spot. Now, those of you who know about temperatures in degrees Kelvin, this is about minus 120 degrees Celsius. So out at Saturn, that's construed as quite hot. So we had this real high hotspot at the south pole. You put these 2 data sets on top of each other, and the hottest spot was right over one of the cracks. So the implication is that internal heat is leaking out from Enceladus. So you had water vapor coming from potentially from a liquid water ocean under the surface, and you had internal heat leaking out. Now, one of the things as a planetary scientist that one tries to get an understanding of is are there other places in our solar system and beyond where life might be able to form? We talk about searching for potential habitability. You need there to be 4 things. You need there to be liquid water. You need an internal heat source. You need organic material. And then you need those first 3 ingredients to be stable enough over a long enough period of time that something can happen. So we had 2 of the ingredients. This is data which was taken by an instrument called the ion neutral mass spectrometer, which this is a view taken from the imaging instrument, which shows you what the plume looked like when we got really close. So as we flew really close to Enceladus through the plume, this instrument was able to essentially measure what was in the plume. They found water vapor, which we knew because we'd seen that in our data. They found methane. They found carbon monoxide and carbon dioxide, but the most important finding was they found organic material in the plume. So we essentially had those first 3 ingredients that you need for life to potentially form. The outstanding question was and still is, have they been stable enough over a long enough period of time that something can happen? But it was really, once this discovery was made, the focus of most of the rest of the Cassini mission moved to Enceladus, and we had about 125 hours of Enceladus as a result of that, getting an understanding about Enceladus. And that's when the gravity data confirmed that there's actually a global water ocean underneath the surface. Let me talk a little bit about Titan. This is one of the other moons of Saturn. It's the reason we were interested in Titan, and I told you right at the start that not only did Cassini orbit Titan, but the Huygens probe traveled down onto the surface. One of the reasons we were interested in Titan is that we think its atmosphere, the chemistry in its atmosphere, was very similar to our own atmosphere when it first formed. So it's almost like a way of going back in time and seeing what the atmosphere was like. But before Cassini reached Saturn, we'd never seen down onto the surface. That's because there's this almost high orange hydrocarbon haze, which doesn't allow you to see down onto the surface. A bit like a really smoggy city where you can't see through the smog. But one of the things you can see, this is from a Voyager spacecraft image, is this blue deep region here is the deep atmosphere. So Titan is the only moon in the solar system that has a very deep atmosphere, about 170 kilometers in depth. And that's the atmosphere through which the Huygens probe traveled down. This here is a view which was taken by an instrument which looks in the infrared. And one of the surprises when we first went into orbit around Saturn is, based on the Huygens probe images, it was clear that liquid had flowed on the surface of time. And so the Cassini spacecraft kept looking to see if they could see liquid on the surface. And for the first couple of years, they couldn't. And then finally, this instrument saw a glint of sunlight or one of the oceans, or one of the lakes rather, at the North Pole. And it took us a while to realize why we hadn't seen it before, and that's because it had been the dry season on time. There hadn't been any rain up to that stage, and then suddenly the season changed and liquid rained down on the surface. It's not liquid water though, it's ethane and it's methane, so it's a very weird place. And this shows you our understanding now of the surface of Titan. If you compare back a couple of slides with that orange hydrocarbon haze, here you can see how much better we were able to do. This was not done by the visible camera. It was done by the infrared camera, which could see through the haze. So let's have a look. This orange region here are sand dunes around the equator. So it's essentially different faces of the moon. The blue region here is water ice on the surface. Here is an ice volcano, which you can see. There's a large crater, which was clearly made by something very hard and large impacting the surface. And if you look really closely, where can you see? You can actually see the lakes at the South Pole. And there are some lakes at the North Pole, but you can't see them quite so well. So after spending 13 years in the Saturn system, we now have a much better understanding of Titan. And it turns out that not only is the surface very interesting, but also there is a liquid water ocean underneath the surface. And this was data that was taken from the gravity instrument on board. It turns out that there is this global subsurface ocean under the surface. So that means there are two moons orbiting around Saturn, which have got liquid water oceans under the surface. This here is our understanding of what the internal structure of the four large moons of Jupiter look like. And this was from data taken by the NASA Galileo spacecraft, by the magnetic field instrument on board that spacecraft. And the three moons that we're going to focus on with the JUICE mission, which I'm going to talk about in a second, is Europa in the top right, and you can see the thick water ocean under the surface. Ganymede in the bottom left, where again, we're almost certain there's this liquid water ocean, and Callisto as well. For me, Ganymede is the most exciting of the three that we're going to, because it's the only moon in the solar system that has its own internal planetary field. So if you stood on the surface of Ganymede with a compass, the needle would point to the North Pole. So there is a magnetic field on Ganymede. You might think, how can a magnetic field instrument measure liquid water oceans? The way in which you can do that is if you've got a conducting body and it's in a magnetic field that's changing, that changing magnetic field will induce electrical currents that flow in the ocean. Those electrical currents generate a magnetic field, and then the instruments that we build at Imperial can actually measure that. And this is a very busy slide, but I think for me, it describes what I think is the most important realization that planetary scientists have come to in the last 30 years. And that is that you don't have to be close to the sun to be able to find liquid water. So let me just describe to you what we're looking at. So here we've got the sort of mass of whatever star we're looking at relative to the sun, and there the sun is there. And on this x-axis here, you've got the radius of the planet, or the orbit of the planet relative to the sun. So here we have the Earth. Inside of the Earth, we have Mercury, and we've got Venus. And then beyond a certain distance called the snow line, any water that you have on the surface is going to be ice. Inside of the snow line here, so I keep using the mouse, inside of the snow line here, any liquid that you have on the surface should be, any water that you have on the surface should be in liquid form. And until about 30 years ago, the real focus was trying to find if there was life in our solar system. And the focus was on the inner planets, because that's where you would expect to find liquid water. the surface. We have now realized with the Cassini and the Galileo observations, you can move beyond the snow line. You can go to Jupiter, where you have moons which almost certainly have liquid water oceans under the surface. And you can go to Saturn as well, where we know that both Enceladus and Titan have got liquid water oceans. And I think the discoveries that we were able to make at Cassini allowed us to persuade the European Space Agency to fly the Jupiter mission that I'm going to talk to you about next. I'm going to come back to Cassini right at the end because it's a beautiful movie that ends the talk off really well. But let me move on to JUICE now. Okay, so this is a view. So if you were standing in your back garden and you could see Jupiter, and you can see Jupiter by looking up at the night sky. If you could see the magnetic field lines of Jupiter, they would essentially fill the night sky. They would be 30 times bigger than the moon. And so this is the environment, these yellow lines are the magnetic field lines of Jupiter, and then this is the environment that the JUICE spacecraft is going to be going to. But the reason I like to show this is it reminds me, my first view of Jupiter and Saturn was in my garden in Durban. My dad built his own telescope. And I remember my sister and I helped mix the concrete for the base of the telescope. And we thought that was the most important part of the thing at all, because the telescope wouldn't have stood upright without it. But never as a kid in Durban did I think that I would end up doing what I'm doing now.
Is the sun on the left?
No, sorry, the sun is way off to the left. That's the moon, just to give you context for size. So if you were looking at a full moon in the night sky, the environment of Jupiter with the magnetic field lines would fill the night sky. But yeah, if the sun was here, it would be way too.
It's the sun that's making it an obstruction.
Yes, yes. So the sun and the solar wind coming in from the left interacts with the magnetic field of Jupiter. And so you have the sunward side here that is much smaller, and then the tail extends way off to the right. Yeah. Okay, so let me talk to you about the JUICE spacecraft. So one of the things, if you're a planetary scientist and you work on outer planets, you need a huge amount of patience. Because we first started thinking about a Jupiter-type mission back in 2008. From my perspective, we're now halfway through the mission. It was launched last year. We'll get there in 7 years' time, and we'll be taking data for another 10 years, hopefully. So at the moment, we're halfway through the mission. But this shows you a view of the JUICE spacecraft. We're using solar power on JUICE. So we have rocket fuel, and it allows us to change the trajectory of the spacecraft, but all the instruments are operated using solar power. We've got 76 square meters of solar panels, and of course, when the spacecraft was launched, the solar panels are folded away, and then after launch, they were deployed. Just like we had on Cassini, we have a high gain antenna, which once a day points to the Earth and sends the data down. There are lots of instruments on board, but for me, the most important instrument, the one that we build, is the magnetometer, and that's on this very long boom. Just like we did on Cassini, you want to get as far away from the spacecraft as you can. And the other antenna that you see here is the radar antenna, this very long radar antenna. So after we were launched, there was a period of time where everything was happening. All the different antennae were being deployed, the instruments were being switched on. And it's a very scary time because you think you've designed the instrument properly and well, but you only know after the launch and after the vibration of launch as to whether it survived or not. Okay, so this shows you a view of the instrument that we built in the lab at Imperial College. So the instrument consists of 3 different sensors at different distances down the boom. The one that we built at Imperial College is this one here. It's a flux gate magnetometer. The one that was halfway down the boom was built by our colleagues in Germany, and it's another flux gate. You always fly 2, so you can calibrate between them, but also so you have redundancy as well. And then uniquely, for the first time, we also flew a 3rd sensor, which is right on the end of the boom. And that doesn't measure the 3 components. It doesn't measure the direction of the magnetic field. It only measures the magnitude of the magnetic field. And that helps us calibrate when we're to our Ganymede. And then the last bit of the instrument is the electronics box, which is this large black box here. The electronics box is on the main body of the spacecraft. All of those long cables that you can see then connect the electronics box to the instruments, which are on the boom. Now, one of the scary things that you do when you're building instruments is you build lots of models and you test them to make sure they work. You test them on a vibration table to make sure they can survive the rigors of launch. And our first model was being tested on the vibration table and one side of it fell off. And so we realized we needed to make it a bit more robust. On the right-hand side here is a view of a shock test. You can see this large hammer that falls on top of the e-box to make sure that it will survive, and it did. But one of the reasons I like to show this is it reminds me that we were building the instrument during COVID lockdowns. And I'm flabbergasted that the teams were able to build the instrument, but also the spacecraft was able to be launched on time. So at Imperial, the UK government closed all universities down and told us to go home. 3 months later, we were able to slowly reopen our labs. And so we were able to come in with social distancing, mask wearing. We were extremely careful, but that meant we were able to continue to build the instrument. This shows you a view of the spacecraft being delivered to French Guiana. So the spacecraft was launched from French Guiana. The reason we launched from French Guiana, it's a European base, it's a French base, and it's very close to the equator, and you need less fuel to get away from the gravitational field of the Earth if you're at the equator than anywhere else. So it arrived on an Antonov aircraft, which you can see here. The way in which you get the spacecraft off the Antonov is you open the nose of the aircraft, and you can see the G spacecraft was in this box that you can see here, and here you can see it being moved out of the Antonov. It's the only aircraft large enough to get the 6-ton spacecraft out to French Guiana. And we're all very nervous. We were watching the Antonov. You can watch aircraft after they've taken off, going to their destination, and the whole team was watching as it was traveling to French Guiana. Because you know it's your baby. You've spent 10 years on it. This is a view of the spacecraft in the launch preparation area. You can see some people standing there giving you an idea of the size of the spacecraft. And as I mentioned earlier, everything is folded away so that we could have launched. These here are the solar panels that are folded away on one side. Here are the solar panels on the other side. Here you'll notice that it's covered with a black material rather than gold, as it was for Cassini. But again, it's a thermal blanket that helps protect the instruments and the spacecraft. And if you look, where's my mouse gone? If you look really carefully here, there were 3 parts to the magnetometer boom. And after launch, the magnetometer boom deployed. And again, it had to be folded away to be able to do that. You can't talk about a spacecraft without showing the launch. So this showed you the launch from French Guiana on the 14th of April. It was due to be launched on the 13th of April, and we were all sitting in the mission control room watching everybody working. And they were doing the countdown, and everything was going really well. And then 10 minutes before the launch was due to happen, they sent a balloon into the upper atmosphere. And the reason you do that is to check and make sure there aren't any storms going on. And on the 13th of April, they saw there was a lightning storm going on. And you don't send a 1.5 billion euro spacecraft into a lightning storm. So it was scrubbed for the day. We went back the next day, and it was a perfect launch, absolutely perfect launch. Those of you who've got good eyesight, if you look really closely, so the spacecraft was in here. If you look really closely, there is a picture, it was a painting that a 12-year-old girl submitted to the European Space Agency. So there was this competition where children could submit pictures of what they saw, what they thought of the JUICE mission was going to do. And this particular picture won, and it shows Jupiter and some of the moons and the spacecraft traveling towards Jupiter. And she was actually at the launch. That was the prize that she won, was to be able to go to the launch. So don't get a fright. It's going to be a little bit noisy. You're going to actually see and hear the launch happening. This is one of the last Ariane 5 launches. Arianespace, that's responsible for these launches, had a new launcher that they wanted to use, and they delayed using the new launcher so that JUICE could launch, because all the instruments in the spacecraft had been designed to experience the launch loads of Ariane 5 and not Ariane 6. But it was a perfect launch. We didn't need to use any extra fuel to get where we wanted to go. So I'm going to talk very briefly about the three moons we're going to focus on. So Ganymede in the top right, it's the largest moon in the solar system. We're almost certain it has a deep ocean, but we will confirm that once we get there. But as I said, it's the only moon in the solar system that has this internal dynamo field as well. And you've got the induced field that you can measure. The one in the middle, Callisto, is the other moon, one of the other moons we're going to. Again, we think there's a liquid water ocean. You can just see it in this pale blue here. But the strange thing about Callisto is its internal structure is very, very different to Ganymede and Europa. There isn't any differentiation that's taking place, and we're not quite sure why. You know, these three moons have been there the same amount of time. Why is their internal structure different? But Callisto has a very old surface, and by examining with other instruments the surface of Callisto, we're going to be able to get an understanding about how craters formed and how the surface of the moon changed. And then bottom right, we have Europa, which again has an ocean. We're only going to fly past Europa twice because it has a very a lot of radiation. It's in an environment where the radiation is very high. To the spacecraft and the instrument, you don't want to spend too much time there. But in fact, NASA is sending a spacecraft called Europa Clipper to Europa, and both of the spacecraft are going to be there at the same time. And that'll be great. You can take 2-point measurements in the system. So let me tell you one of the things I lose sleep about, and that is the measurements we need to make at Ganymede. So the left-hand image shows you a view of Ganymede embedded in the magnetic fields of Jupiter, which is changing. And that changing magnetic field causes electrical currents to flow in that blue ocean you can see. Those electrical currents generate a magnetic field, but the magnetic field it generates is really small. And so the most important thing my instrument needs to do is to be able to measure these very small changes in the magnetic field, because that's going to allow us to work out not only how deep the ocean is, but what its salt content is as well. If that's all we had to measure, that would be fine. But we have to subtract away the effects of the dynamo field at Ganymede. Luckily, the dynamo field is static in time. It's not changing in time. So that's one of the things we have in our favor. And then, of course, it's embedded in the background magnetic field of Jupiter. So it's the only mini magnetosphere inside a magnetosphere, because Ganymede has a magnetosphere as well. And these red ellipse and the circle that you see shows you what the orbital tour of JUICE is going to do. Right at the end of the mission, we're going to go into this close circular orbit, which will hopefully allow us to resolve these induction signals. One way of thinking about it is you're looking for needles in a haystack, and they change in shape and color all the time. And that's what I usually think about. Our instrument can measure it, but it's whether we can subtract these other effects away to let us do it. So before I move on to the end of mission for Cassini, let me just talk about the fact that from my perspective, we've come a really long way, but it's using knowledge that we gained from way back in 1610. Galilei built his own telescope, and through that telescope, he saw the large moons of Jupiter. We have had a mission to Mars where there was clear evidence of liquid water having had been on the surface. We have made measurements in the deep oceans of the Earth, where the pressures and the temperatures are so extreme you wouldn't expect to find life, and they found bacteria. So this is potentially what we're looking for at the moons of Jupiter. And then we've had an exploration phase where Galileo explored Jupiter and its moons, Cassini explored Saturn and its moons. We then discovered the first extrasolar water world. And now, from my perspective, we're in the characterization stage. JUICE, ESA's European Space Agency's JUICE spacecraft, and the NASA Clipper mission are going to allow us to really characterize these ocean worlds and allow us to, in the future, potentially land on the surface of one of them. You know, one of the things I get asked quite often is, why don't we just send the lander now so we can get under the surface and check what's in the liquid water ocean? But where do you land? You don't know how thick the ice crust is. You don't want to land in a region where the ice crust is 100 kilometers in depth, because then you can't get under to the ocean. So that's one of the things that we're going to characterize. So for the last part of the talk, I just wanted to go back to Cassini and just describe to you the end of mission for Cassini. So we had planned to spend 4 years orbiting around Saturn. The instruments in the spacecraft continued to operate beautifully, so the mission lasted 13 years in total. But it was clear that we were going to run out of fuel, and we wanted to make sure that we didn't crash land on one of the moons where there is liquid water. So this is what we did. In the last year of the Cassini mission, we had two different phases to it. We used Titan and the gravitational field of Titan to get us out of the equatorial plane into what we for the first 6 months, it was these ring grazing orbits. Oh, sorry, I didn't mean to do that. So these white orbits were the ring grazing orbits, where the closest approach was just beyond the edge of the visible rings. We took data there for 6 months, and then we moved to the grand finale orbits, these blue ones, where we were essentially inside the rings, just above the top of the atmosphere and inside the rings. And then the final orbit is that orange one there, where the spacecraft crashed into the atmosphere of Saturn. And this gives you a view of what the orbits looked like. And the reason I like to show this is that it just confirms that the rings are not solid. They look solid, but they're not. They're made up of countless individual particles, each in their own orbit around Saturn. And we were taking a real chance here, because we didn't know if this region here was clear of material or not. So we could have lost the spacecraft on that first orbit. And we were getting closer and closer on each of those blue orbits until, as you can see, that orange orbit, we burnt up in the atmosphere of Saturn. Now, one of the reasons we did this is that we wanted to try and understand the internal planetary field of Saturn better. The way the planetary dynamos work, the way that internal magnetic fields are generated, is you need an overturning motion, a bit like porridge bubbling on the stove, and you need a rotation. That's the planetary dynamo. But also, planetary dynamo theory suggests that the rotation axis of the planet and the magnetic axis need to have an angle, need to have a tilt between them. If you don't have that tilt, you can't continue to generate the magnetic field. And all the measurements we had taken in the 13 years before this had said to us there was no tilt at all. And we didn't understand that. We thought maybe the internal dynamo was dying, and this is what the magnetic field was telling us. So it was agreed that we would do this end of mission orbital tour so we could get as close as possible and see if we could try and understand the magnetic field. And it turns out the answer is there isn't a tilt. And that's because there's a secondary dynamo above the deep internal one, which is masking the effects. But we needed to get really close to be able to work that out. So this is an artist's impression of the view of the first close flyby. And I remember I went to the Jet Propulsion Lab for it. We were all terrified because we didn't know if it was clear or whether there would be energetic dust particles that would kill the spacecraft. And I remember meeting the mission manager, and he was looking very nervous. And he said to me, "I'm very nervous, but I should be more nervous because my instrument was on this long boom. I wasn't protected by the high gain antenna at all. But it turns out we didn't have to worry. It was completely clear of material, and we were able to do these final 22 orbits." This shows you where Cassini burnt up in the atmosphere of Saturn. So this was from the infrared instrument. The red that you can see is internal heat leaking out from the interior of Saturn. And that's where Cassini went into the atmosphere. And that gives you context. It was just above the equatorial plane in the northern hemisphere. This shows you a view from the mission control room at the end of the mission. And it was really interesting, you know, those last 6 months were exhausting. We had a close flyby of Saturn every 6.5 days. And it was getting to the stage where we just wanted it to be over. We just couldn't keep up anymore. And then at the mission end, you suddenly realize that's 25 years of your life, you know. And then it's almost like losing a family member. So this brings a sort of almost tears to your eyes to see this. But for me, the most poignant moment was this one here. So if you look at this data in the top left here, that spike there is telling you that the spacecraft is talking to the Earth. When the spike disappears, it means the spacecraft is no longer talking to the Earth. That spike disappeared, and then it briefly came back again. The reason it came back again is no one had told the spacecraft it was end of life, and the spacecraft had been trained to move itself so it could point to the Earth. So it moved itself for one final message down to the Earth, and then it began to tumble and it broke up in the atmosphere. So for me, I think that was the most poignant one. So I'm going to end by playing a video which was put together by NASA 6 months before the end of the mission. And everything that they said would happen at the end of the mission happened. So let me play that for you. I'll stop there. Thank you. Wow, that's quite a flex away. Thank you very much. Questions, please. We have plenty of time for questions. George.
Brilliant work.
Thank you.
So you had one slide where you said there was light organics and then more complex organics. What did you mean by more complex organics?
So the simple organics is nitrogen and carbon, and the complex organics is a combination of those, so molecules, and I can't remember exactly what they were. Combination.
But they're simple combinations.
Yes, yeah. So my understanding is the simple organics was just the building blocks
Yeah,
for organic
yeah.
material, and then the complex ones is the combination, so which is essentially the simple.
Nothing like a protein or anything.
No, nothing like protein. No. But I don't think that instrument would have been able to measure proteins. They're sending a new mission to Enceladus in the future, and there they will build instruments that will be able to measure.
Is anything like an amino acid?
No. But again, we need to build instruments that will do that.
Well,
We know, well, lots of questions, but one question is, you know, the moons of Saturn or Jupiter, do we know that they will form around the same time, or how do we know what
That is our
history?
That is our understanding, that they formed at the same time. So that's why it was such a surprise that Enceladus is still having internal heat source, because it's small, and we would have thought as it cooled down since it first formed with all of the other moons, it shouldn't have that heat source. So there's something that is.
And are they so different then because they're at different locations?
Yeah, I mean, there was one of the moons of Saturn called Iapetus was a captured moon. That was the very funny looking one that they showed right in that final movie. That we don't know. Whereas our understanding of how the planetary systems form is they did form at about the same time.
So what does the existence of this water under the surface tell us about the formation history of these objects?
Well, for Enceladus, the fact that there's still this internal heat source means that it was probably there were probably tidal forces that were acting on it. So its orbit around Saturn is almost circular now, but it probably wasn't circular in the past. It was probably elliptical. And so on some parts of the orbit, it was closer to Saturn than on others, so the gravitational force. So that's the thought of why there was potentially still heat. But you know, the fact that it's losing a lot of water vapor, you wonder how much longer it's going to continue to be able to lose water vapor for the ocean.
Even if it's full, precious. Oh, no, I'm going to put it in that. The lid. The tin's there, that's.
So we should try and take a question from the.
There's some in the chat.
Oh, yes, there's two who want to take the.
It's just.
We have the expert.
Yeah. Or can you tell us what it says in the chat? Have you got?
Well,
Just press on that.
let's need to speak up. So please repeat the questions and
Okay.
please repeat the questions into the microphone. So I was the one asking whether the audio was still a problem, but the impression that I get is that when somebody asks a question from
The floor.
from the
they-
floor,
Okay,
You
so
need to repeat the question.
I can't.
Yeah.
So Patricia, you asked a question about
Well,
why there is still potentially, why there's potentially liquid water.
liquid water. Yeah.
And so my answer is that our understanding is that it's tidal forces on the moons that are keeping the interior warm. And so their orbits are not perfectly circular, they're elliptical. And so in some parts of the orbit, they're closer to the planet than on others. And so the gravitational force is stronger. And so therefore it's tidal forces that are keeping the interior warm. Yeah. Yes.
Yeah.
Is there any reason why the ocean moons around Neptune and Uranus?
Sorry, say that again. I was listening to what it was.
Is there any reason why we wouldn't find water types around Neptune and Uranus?
No.
So the question was, is there any reason why we wouldn't find these moons, this type of moon around Neptune and Uranus? You can repeat your answer.
Yes, we think there are. So my answer is no, we would expect to find it. And so we think there are these water worlds around Uranus and Neptune. And there are NASA plans for potentially to send a mission to Uranus. I went to a meeting in Washington about this about 6 weeks ago. And I was all engaged and excited, and then they told me the earliest they could launch was 2040. And it would take 40 years to get there. They began to lose interest, I must confess. I know that I shouldn't do that. I should be building for the future, but I did lose a little bit of interest there, I must confess. One of the things I didn't point out when I was talking about Ganymede is that we think Ganymede is a water world. And we think there are lots of extrasolar planets that have got water worlds in orbit around them. So by understanding Ganymede, we hope to be able to understand some of the extrasolar water worlds. I probably shouldn't have confessed the losing interest, but should I?
Stay in the room.
Might be questions in the chat, I don't know.
Any questions in the chat? Yep, we have.
Why the lack of creditors on syllabus? Because it's how did it evolve? But could it be possible that the spray from the geysers falls over the surface and obliterates the small ones?
Yes, it is possible. So
Repeat that.
So the question is, and those people who are online should be able to see in the chat, the question was about the young surface of Enceladus, and I'll tell me if I get this right, whether the geysers, the water vapor geysers are falling back, whether material is falling back on the surface, and it is. That's why it is being resurfaced, is that the material is falling back. And in fact, some of the moons that are orbiting close to Enceladus have also got water vapor falling back on the surface as well. And it also is helping form the E-ring.
So was it very lucky that you decided to do that very close flyby around the particular pole that you did?
Yes.
Would you have missed it if you'd gone to the other pole?
Well, what I find interesting is those two early flybys were quite distant. And the first one, the 1,300 kilometre, was actually over the North Pole.
Yes.
But we saw enough of a signal in the magnetic field that we thought something was happening. We would have probably found it later on in the mission.
But not as spectacular.
But not as spectacularly, yeah.
Another question, Ronnie asked, he understands that the Earth was he understood that the Earth was in the Goldilocks zone or lifespan.
Yes.
But now things are discovered outside of that. We have much of it, just thoughts on the Venus.
So I think the question was about the Goldilocks zone, which is a zone in which we think life can form. And the Earth, of course, we're looking at ourselves, is in the Goldilocks zone. So that for me is, I think, the most important realization we've come to in the last 3 or 4 decades, is that if you're searching for liquid water, which is where people have always thought the Goldilocks zone would lie, you can go much further away from the sun and you can find liquid water, but it's underneath the surface. So I think for me, that's one of the most important things we've realized. And that slide that I showed, that rather complicated slide, we presented that to the European Space Agency when we're trying to persuade them for us to take the mission to Jupiter. And I think that was part of why we were able to persuade them. And there was a question at the back.
Yeah, I guess maybe it is the same question. We didn't know that there was liquid water to be able to send a mission. So how did you discover liquid water? It's not outgassing.
It's by measuring what's in the atmosphere, is my understanding. And so they can remotely measure what's in the atmosphere of exoplanets. No, it was an exoplanet, not a moon, that I was talking about.
This is the question about detecting water on exoplanets or on exoplanet moons.
Yeah, no, that first exoplanetary discovery was on a planet rather than a moon. Yeah.
Sorry, that doesn't answer my question.
Okay.
The question was, liquid oceans, are they sort of just above 0 degrees, or they just, there must be something between 0 and 100 Celsius? Oh, big range.
We're not sure. We think the high pressures in the area are going some way towards ensuring that you can have liquid water, because you would expect at these distances and right in the surface. Sorry, can the people who are talking online mute themselves? Thank you. We think it's due to high pressure in the interior. Ganymede is a real surprise, because we think there's this deep ice layer, and then there's a liquid layer, and then there's another deep ice layer. And that has to be some combination of pressure and temperature to let us do that. And people are trying to do modelling on the Earth to see if they can understand how that might happen. So we don't have the answers to that. No.
Yes.
I read an article in about 2004 about the Hankins program. Can you tell me if what I'm going to say is true or not? Apparently, it was going to be about 5,000 kilometers away from the mothercraft, where it was beginning to type. But the engineers realized that the signal, the lock onto the signal, was probably problematic. So they changed the relationship. They changed it to be about 50,000 kilometers from the mothercraft.
So the comment from the back was that the original plans for the release of the Huygens probe was it was going to be, the release was going to be 5,000 kilometers away from Titan when it was released. But they did some modeling work en route, and they realized they hadn't taken the Doppler shift of the signal into account. And so they actually changed when they released it, and it was released when it was 50,000 kilometers away. It's a good thing they tested it out before they got there, is all I can say. Yes, yes. Very good. You know, almost a bit like using inches instead of centimeters, which one of the NASA spacecraft did. And
Yes.
it didn't end well. Yeah, yeah, yeah.
Anything else online there?
And for you?
Why don't you get rid of the stop share? Why don't you stop the share?
Do you know stop the share? I think I just have to click. Oh, hello, Trish.
Oh, and Manfred Halberg. Hello, Manfred. Sorry, I'm recognizing names on screen. Manfred was one of my professors when I was an undergraduate.
Oh, indeed.
Yes.
He's been very active in educating us for long since.
Absolutely. Yeah.
Hi there, Michele. It's lovely to hear your talk again. Really enjoyed it.
Thank you, Manfred. Thanks for joining.
Thank you.
Dennis Engel's brother is in the audience.
And Manfred, Dennis Engel's brother is in the audience.
Oh, great. He was at school with me. Yes, what I mean.
It's a very small world, you know.
Okay, I think we can end then. That's tour de force. It sounds like a very exciting project, and I think we can't wait to hear what's going to happen next.
Thank you very much.
Thank you very much indeed.
Thank you very much.
Thanks to everyone for joining us, those here and those online.